Welcome to my classroom. In this video, I talk about two problems on posting: how to post a diamond safely and how to toss a coin through posting fairly. Both problems reflect some ideas of cryptography. Euler's theorem and Euclidean division are mentioned and illustrated with an example. A book is recommended at the end of the video. Here is the first problem. Sarah and David live in two towns far away from each other. They can only communicate by post. David wants to send Sarah a diamond. He buys a box and a lock. He puts the diamond in the box and locks it. David sends the box to Sarah by post. Suppose that the post office inspects all posts which can be opened and take away all valuable things other than letters. How can Sarah get the diamond? Pause the video and think about it. When I talk about this problem in my real classroom, I receive some interesting ideas from my lovely students. I don't know what is yours. As I suggested in my previous videos, very often we have different ideas and methods for the same problem. It is a good practice to think actively and openly for the same question. Here, I provide a solution from a book which I will talk about it later. The box is locked by David and it is sent safely to Sarah. Sarah cannot open the box as she doesn't have the key. What she does is to add another lock to the box and sends it back to David. The box is double locked. The diamond is safely kept inside the box. David removes his lock by his own key. The box is still locked by Sarah's lock. David posts the box safely to Sarah. When Sarah gets the box, she can unlock it by her own key. In this way, locking the box with two keys and sending the box 3 times, Sarah gets the diamond from David, and the problem is solved. The second problem. This time, Sarah and David are given a ticket of a free trip for a single person. They want to decide who will get the ticket by a fair method, like tossing a coin. How can they do it by posting? Pause and think for your solution. Here is a solution. One of them, say Sarah, defines a one-way function. That means a function that is easy to compute in one direction but difficult to work in the opposite direction. That is, hard to find the inverse function. Let fx denote the one-way function used by Sarah. Sarah sends the function fx and a number 8 to David. David is asked to tell the parity of the last digit of f inverse a, that is, even or odd. It is agreed that if David gives the correct answer, he gets the ticket. Otherwise, Sarah takes the ticket. Since fx is a one-way function, David is not able to find the inverse function. He can only make a wild guess like tossing a coin for the answer. David sends his answers to Sarah. As the function is defined by Sarah, she knows the inverse function. Therefore, she is able to find the last digit of f inverse a and determine whether David's answer is correct or not. Sarah tells David who gets the ticket and also the inverse function so that he can verify the result. In this way, the decision is fairly made to both of them. Choices of one-way functions are plenty. A simple idea comes from the fact that multiplication is easier than factorization. Given two primes p and q, it is easy to multiply them to get n. However, given n, particularly when n is large, it is difficult to factorize n for p and q. Another idea is based on the fact that substitution is easier than solving equations. Consider the equation a to the power n congruent to c mod b, where a and b are constants. Given the value of n, it is easy to get c. But given the value of c, it is hard to find n when a and b are large numbers. I will give a third example of one-way function using Euler's theorem for Sarah's choice. Euler's theorem states that if a and n are relatively prime, then a to the power phi n is congruent to 1 mod n, where phi n denotes the number of positive integers less than n and relatively prime to n. I'm not going to prove this theorem, but talk about some basic properties. Here, two numbers a and n are relatively prime, means that they have no common factor other than 1. It is equivalent to say that their GCD, greatest common divisor, that is, their highest common factor, is 1. In notation, rewrite this. To understand more on this notation phi n, let us check with some simple examples. For n equals 3, since 1 and 2 are relatively prime to 3, so phi of 3 is 2. For n equals 4, 1 and 3 are relatively prime to 4, so phi of 4 is 2. For a prime number p, p is relatively prime to all positive integers less than p. Therefore, phi of p is p minus 1. Note that phi of a times b equals phi of a times phi of b. You may prove this property on your own. So, phi of 12 is equals to phi of 3 times phi of 4, that is 4. Actually, 1, 5, 7, 11, these four numbers are relatively prime to 12. Coincides with what we have done. When n is a prime, the statement can be rephrased as, if p is a prime and a and p are relatively prime, then a to the power p minus 1 is congruent to 1 mod p. This statement is known as Fermat's little theorem. In other words, Fermat's little theorem is a special case of Euler's theorem. We learned how to find the GCD or HCF of two numbers in primary by division or by factorization in Form 1. Actually, we have another division method for finding the GCD. We call it as Euclidean division, 輾轉相除. Let me demonstrate this division by an example. Find the GCD of 11 and 72. In notation, rewrite. First, divide 72 by 11. Then, divide 11 by 6. Divide 6 by 5. Divide 5 by 1. The last non-zero remainder is the GCD. The answer is 1. That is, the GCD of 11 and 72 is 1. I think this answer is obvious before calculation. Why bother the troublesome division? With the result shown in the Euclidean division, we can find two integers h and k such that 11h plus 72k equals 1. From the Euclidean division, we can put down the division step by step. Then, by backward substitution, we can work back and get the values of h and k. That is, h equals to -13 and k is 2. This result applies to general situation. Given two positive integers a and b, by Euclidean division, we can find the GCD, say d. Using backward substitution, we can find two integers h and k such that ha plus kb equals d. This result helps us solve the following modular equation. 11x is congruent to 1 mod 72. Note that this 1 is the GCD of 11 and 72. By the previous result, we have x is congruent to 59 mod 72. The solution. Now, back to Sarah's one-way function. Sarah chooses two big primes P and Q, and let n equals P times Q. We have phi of n equals P minus 1 times Q minus 1. Take h less than phi of n, and h is relatively prime to phi of n. By Euclidean division, and as shown in the previous example, we can find k such that h times k congruent to 1 mod phi of n. Now, define the one-way function. Let f of x is congruent to x to the power h mod n. Then its inverse is x to the power k mod n. Why the inverse function is given by x to the power k? It can be checked by using Euler's theorem. I leave the verification for you as an exercise. So, Sarah sent the function f of x and a number a, which is relatively prime to n, to David. David is not able to find p and q, and so as phi of n. That is, David cannot find the inverse function. He can only make a wild guess, like tossing a coin for the parity of the last digit of f inverse a. After David chooses its answer and sends it back to Sarah, Sarah can tell who will get the ticket and send the inverse functions to David to confirm the decision is fairly made. Here, n, a, and h are given to David. They work like the public key. P, q, and k are kept by Sarah, and they are the private key. You are encouraged to choose some numbers for setting a one-way function and work out the calculation by practicing the techniques of Euclidean division, solving modular equations, and use of Euler's theorem in order to have a better understanding of the concept and techniques mentioned above. I hope you find these two little problems interesting. They come from a book, In Code, A Mathematical Journey, written by Sarah Flannery and David Flannery. Actually, Sarah's is David's daughter. This book is mainly about Sarah. The book talks about how David cultivates Sarah's interest in mathematics since she was a kid. Sarah loves challenging problems. She participated in a science competition in Ireland, then Europe and United States. The book describes how she took up the challenges and captured the prizes one after the other. The book was written when she was a teenager, and it was an encouraging story. I recommend the book to both teenagers and parents, for those who want to learn better and those who want to help their kids to learn better in mathematics.